Okay, good morning. Hello. Today's topic is hypothesis testing, and that's the same statistical testing or hypothesis testing that you know from undergrad statistics, but it may look a little bit different because what we are aiming for here in the first part is kind of a general description of the hypothesis testing framework, and then later on we look at some specific things. But before we start, who has studied and performed a t-test? You guys, you haven't seen t-tests? No?
Performed, but not quite know how the mechanism inside.
Okay. So for those who did, could you, one of you, explain the logic of the t-test, please? Who volunteers? I mean, specifically the psychologists who've all learned, and the thing is there are more psychologists than non-psychologists in this room. How does a t-test work? What's the basic idea here? I want to hear what you learned in undergrad statistics.
Not much about the mechanisms behind it.
But what did you learn in psychology about t-tests?
Mainly we do t-tests for group comparison.
Mm-hmm. And how?
We have two groups and want to compare them.
Okay. So that would be a paired sample t-test, I guess. You can also do one sample t-test where you compare against one group against some value. Actually, a paired sample t-test is based on the differences, and there's a one sample t-test after all. And so what's the basic logic behind a t-test?
We compare the mean of both groups in this case, and then we look if a certain significance is reached.
And what does that then mean?
If we have to reject or accept the alternative hypothesis or null hypothesis.
Mm-hmm. And what's the basic idea, or maybe someone else, what's the basic idea behind null hypothesis testing? So in terms of probabilistic modeling, I just wonder how much you know about this.
I just know, like for t-tests, it would be that there is no difference in the mean values.
No, that's always the strange language that is used in psychology statistics. Yeah, there is no difference in the mean values. Anything else? Okay, so the basic logic, which I would hope one learns in undergrad statistics, is that you essentially create a null model for null probabilistic model for what you're interested in. So you measure something, then you start to think about if the data would be purely random, that's my null model, how likely would it be to observe the data that I have observed? And if this probability, or to observe data that is more extreme than we observe data, is very low, so that's then p-values, then you would say, okay, then the null model maybe is not right, but some alternative model is right. So from my perspective, that's the basic logic. So, which of course from an experimental perspective, you also often, or people often do them in terms of permutation tests. So they, for example, shuffle the conditions, whatever that means, but they, and then they look how likely their data is. So they create a null distribution based on the data. We will look at that in permutation tests, but the basic thinking is under a null model distribution, how likely is my data? If it's very unlikely or doesn't have a high probability, then maybe the null assumption, the null probabilistic model is not right. So that's the kind of basic idea of null hypothesis testing. Yeah, and we will now look at hypothesis testing in, of course, and of course, just what I just said is also from the frequentist perspective, and we will look at hypothesis testing following our hierarchy here. So it's the last thing that we do in this classical frequentist parametric scenario, where we looked at point estimates, looked at confidence interval estimates last time. And when we went from point estimates to confidence interval estimates, we basically allowed for higher probability of being correct while being less precise about our statement about the parameters. With the point estimate, we know we have a very precise statement about what the unknown parameter is, and we have very low probability that we're actually correct. Here we have, we can have a high probability to be correct if we resample data, so 95% confidence intervals, but we are less precise in our statement about the true but unknown parameter because we allow for a whole range. And one can basically, and this is the viewpoint we will take here, also think about hypothesis testing from this idea of making statements about the parameter. And here we will basically just make a statement in the sense the parameter is in this one subpart of the parameter space, which we call null hypothesis, or the parameter is in this other subpart of parameter space, which we call alternative hypothesis. We will look at this and give precise definitions in a second, but you can already think, for example, a null hypothesis in the sense that the parameter is exactly 0. Then you have the alternative hypothesis that it's not 0, so it's all the other possible parameter values. So you have very big subsets of parameter space for which you, with a certain probability, make these statements. So from my perspective, hypothesis testing is it's actually not getting much better than confidence intervals in terms of the probabilities, but it's getting definitely even less precise about the parameter than confidence interval estimates, because confidence intervals are only intervals. And then these hypothesis tests are really big parts of parameter space, but we will look at that. So what I'm trying to say is that you can view hypothesis tests also from the perspective of parameter inference, as we will see. And that's important because from my perspective, hypothesis tests and p-values are what everybody thinks of when they talk about classical statistics. And then there's a lot of debate, are these good things, are these bad things? And one can take kind of a more relaxed viewpoint in saying, well, that's just another form of parameter inference, and it's like confidence intervals, point estimates, Bayesian inference, it's just one form of parameter inference. So this is where we take the stuff from. So some part is actually from a paper that we recently wrote on statistical testing in neuroimaging, for which I had to review substantial amounts of basic mathematical testing theory with the aim of actually establishing a proper multiple testing scenario. So the point of that paper was not so much the testing per se, but the multiple testing. We will not talk about multiple testing here. But if you want to learn about multiple testing, have a look there. Then there's some Wassermann in it. We will talk, and this is also something interesting, that talk about the duality of hypothesis testing and confidence intervals, because that's actually something that's, I think, maybe the oldest thing I ever learned about statistics, because that's what I learned in my third medical year, so around 2002, when we had a statistics course in medicine, and we did I think we did ANOVA by hand or something, and at one point the professor explained that statistical tests and confidence intervals are the same thing, and I didn't quite get it at that point, and then it was always something that I wanted to look up, and now finally, 20 years later, almost, I finally established that. So who has heard this, that confidence intervals and statistical tests are basically the same thing? No? Well, I learned that in medicine, strangely enough. but I didn't understand at that point. P-values we will talk about because P-values are all around, and then there's a link here to a very nice collection of articles in the American Statistician. It's around 25 articles that all discuss hypothesis testing in P-values in contemporary statistics. You also see the kind of how it's called, so a world beyond P smaller than 0.05, because as you might be aware of, there's some debate about, I would rather say about the interpretation of p-values and the finding of a p-value being smaller than 0.05 as being evidence or being, well, that's how it's titled. Have a look. It's a very nice collection of articles, very contemporary, very parts are very advanced, other parts are not very advanced. About this world beyond pure P 0.05. It's not so much about that there's a fundamental problem with p-values or null hypothesis significance testing, so hypothesis testing. The problem that exists is that p-values and hypothesis tests are used a lot in medicine, biomedicine, so in all kinds of biology, biomedicine, when people do studies on whether certain drugs work. So of course also used a lot in psychology and economics. And the problem comes from the fact that people tend to interpret p-values, so in interpreting a significant p-value, so a p-value smaller than 0.05, as if not as evidence, but they then think, or some people think, maybe not even the researchers, but some people then think, okay, this is now the truth, yeah, and this is where the problem comes. It's not even so much the precise interpretation of p-values as frequentist statistics or Bayesian statistics. That also doesn't matter. The problem is that people who read the scientific literature and work with it have a tendency to think if statistical significance is reached, that truth has been established. And of course, that's not the case. It's just a small p-value or a high t-value. What this means is a high signal-to-noise ratio in the observed data based on the current analysis and so on. But it doesn't mean that some form of scientific truth has been found, because there will never be any form of truth, because the unknown, the true but unknown parameter value by statistics will never be discovered. Yeah? So the problem with p-values and hypothesis testing, and why there's often debate about it, has nothing to do really so much with statistics, but more with a misunderstanding of science in general, that people think by doing some data analysis you will learn about the truth of the world. That's the problem. Anyway, have a look at this article collection. That's very interesting. I'm personally, I don't have a big problem with p-values or statistical testing if you interpret it as a measure of the signal-to-noise ratio of your data under the current data analysis. And that's it. Yeah. Good. So the outline today then is to first talk about some foundations. So that would be hypothesis testing from a general mathematical viewpoint. So the mathematical statistics of hypothesis testing, which is a general viewpoint on hypothesis tests, under which you can then study all different forms of hypothesis tests or statistical tests. I will use all these terms interchangeably, so test, hypothesis test, statistical test all means the same to me. Then we will look at some examples, t-test, wall test, and if time permits, likelihood ratio test. Once we have done this introduction to tests, we will look at this duality between confidence intervals and hypothesis tests, because we last week obviously discussed confidence intervals, and then it's nice to link this explicitly to hypothesis tests, so that essentially, when you study these two concepts, you are aware of their connection, and then in a way you also don't have to, you save some cognitive energy because it's kind of the same principles. And then in the end we discuss p-values, because you also find them always in the literature. Good. Questions about these general remarks in the outline right now? No? Good. Then now foundations. So this is again kind of this definition theorem approach to have a precise language about what hypotheses are, what tests are, what test statistics are, and so on. And of course, we are still in the parametric setting, so we are dealing with a parametric statistical model that governs the distribution of a random sample X, which comprises these random variables, which each model individual data points. We assume that there's a PMF or PDF P theta, and X should be the outcome space of the data, so that one observation of this random sample, so for example 10 data points, is an element of this outcome space, and we have as big theta the parameter space of the model. Yeah, so this is the standard assumption we had basically for all kind of parametric approaches we've discussed so far. And the question is now, what are then test hypotheses? Without specifying yet what a test is, we want to specify test hypothesis. If we're talking about test hypothesis, we consider a partition of parameter space. So we have this parameter space, and by a partition, of course, we mean that in this case actually a binary partition, so a two-element partition. We mean two sets, theta 0 and theta 1, that if you form the union, you get the parameter space, and if you form the intersection, you get the empty set. So they are two. Yeah, it's a partition of the parameter space, denoted by big theta 0 and big theta 1. A test hypothesis is then a statement about the parameter governing the distribution of the random sample in relation to the parameter space subset big theta 0 and theta 1. And more specifically, H0 stating that the true but unknown parameter is in the parameter subspace big theta 0 is referred to as null hypothesis, and the statement theta is in the parameters subset big theta 1 is referred to as alternative hypothesis. Yeah? Of course, you need to decide what theta 0 and theta 1 are for a given test procedure. The important thing is, if you set up a test or you study a test, you need to think about what is the parameter space. Then there will always be a partition of the parameter space into one subset theta 0 and one in subset theta 1. And then these statements that the true but unknown parameter is in either one of them are referred to as null hypothesis and alternative hypothesis. One thing that is important here, because we will discuss what is actually known as Nyman-Person hypothesis testing. We will assume that both the null and the alternative hypothesis exist. The reason that we are discussing Nyman-Person statistical testing is essentially because we are also interested in power calculations. When we get to that, I would say, well, we are not really looking at the details of power calculations, but if you are in a context in biomedicine or psychology where people say we need higher power in our study, then they want to compute power for tests. And you can only compute power for tests if you make a specification of the alternative hypothesis. This is what Nyman and Person introduced like in the 1930s. There's another framework that was introduced earlier by Fisher, which under which there's no alternative hypothesis, hence also no power analysis, and there's only a null hypothesis. This, from my perspective, there's a nice paper by Gerd Gigerenzer on Nyman-Person versus Fisher hypothesis testing. I didn't put a full thing in here because it also takes time to explain that. If people talk about power, then there is an alternative hypothesis, there is a null hypothesis, and all these terms, we will see that on a slide later, in terms of rejecting the null hypothesis or accepting the alternative hypothesis and so on, they exist. So in psychology, I've heard that you are not allowed to say, we accept the alternative hypothesis. Have you heard that? No? Good. Then you are, then it wasn't as bad as it sometimes can be. So sometimes, but this only refers to the Fisher testing. So in our, what we're talking about, null and alternative hypothesis scenario, hypothesis exist. One thing that is important is that the null hypothesis is not necessarily the hypothesis that big theta 0 is 0. So this can be a null hypothesis, but it doesn't need to be the case. So in terms of null models, the null model can also be a null model that is centered on some other value. And the null hypothesis is just the hypothesis then one is willing to reject, but that it also doesn't really matter. So the important thing is you do a partition of a parameter space, and in general the null model relates to theta 0, and then you have these test hypotheses. We can specify hypotheses a little bit more, namely to differentiate simple hypotheses from complex hypotheses. So a simple hypothesis refers to a subset of parameter space that contains only a single element. So that would be theta 0 equals the set that contains only a single value, theta 0. And we're mainly talking about scalar parameters here, although this doesn't need to be necessarily only a scalar case. While composite hypotheses refer to a parameter space containing a subset of parameter space that contain more than one element. For example, the null hypothesis of that a given parameter is smaller or equal to 0. So that would be then a null hypothesis that does not have only a single element but multiple elements. So note that so the statement that the true but unknown parameter is in theta 0 is called null hypothesis, but I will also call then just theta 0 the null hypothesis, because it's a little bit redundant to say that all the time. This null hypothesis that theta 0 comprises only the 0 element is an example of a simple hypothesis, and it's also referred to as nil hypothesis. So if you want to be careful and distinguish null hypothesis from null hypothesis from the fact that actually the statement about the true but unknown parameter is that it's 0, then you have a new term, namely nil hypothesis, that you can use in the latter scenario. So these were hypotheses. Any questions about hypothesis? No? Then a test. What is now a test? A test exists in this hypothesis scenario statement, so this is why I introduced this before. So you have a parameter space, you have partitioned it, and now you, based on this scenario, you can talk about a test. And a test, or a statistical test, or a hypothesis test, like I said, all the same thing, is a mapping from the data outcome space to the set 0, 1. Yeah? Formally, phi x takes an element of the data outcome space, maps it to 0, 1. This element of the data outcome space is mapped onto phi x of x. Let me explain this notation, because also our reviewers, or one of the reviewers for the paper, struggled a lot with it, and one can also not use it. One can use it. The important thing that I'm trying to stress here is that phi is a function of a random variable, but for a concrete scenario, of course, phi only maps a data sample, so a realization of the data to 0 and 1. Yeah? So if you think about doing a t-test, what you do is you compute a t-value based on some data, and then you reject the null hypothesis or you don't reject the null hypothesis. And 0 in this case, so the test outcome 0 represents the act of not rejecting the null hypothesis, which is the same as accepting the alternative hypothesis, and 1 represents the act of rejecting the null hypothesis, which is 1 represents the act of rejecting the null hypothesis, which is the same as accepting the alternative. I think I said it wrong here, so I say it again. 0 represents the act of not rejecting the null hypothesis, which is the same as rejecting the alternative hypothesis. 1 represents the act of rejecting the null hypothesis, which is the same as accepting the alternative hypothesis. Yeah? So there are only 2 outcomes. You either reject the null hypothesis or you don't, and the complementary things happen with respect to the alternative hypothesis. The important thing is that when looking and thinking about error probabilities of tests, the test is viewed as a random variable. Why is it viewed as a random variable? Because it's a function of the data. And this I include here with this in brackets x. Maybe in a revision of these slides I get rid of the x, but then this understanding as a mapping also gets a little bit weird, because if it only maps data, so elements of the n-dimensional real number space to 0 and 1, there is no notion of randomness in this, and this is clearly not what is intended. So this is the a little bit of a problem in terms of statistical writing. Either you make it very concise, then it's easy to get lost that things are actually random variables, or you make it not that concise as here, then the notation looks a little bit complicated and might also be confusing. So I don't know what the best thing is. For some time I found it helpful to have this thing explicitly there. This is what I just said. It's always equivalent, and this is the most important thing, because the data are random. The test, and specifically the test outcomes, are also random variables, and you can make statements about the test outcomes. Yeah, of course, if you compute a t-test for one data sample, you only make one decision, reject or not reject, and there's no randomness. But again, you need to think in terms of the frequentist probability setting, that you could do tests again and again and again, maybe even under the same model, especially if you simulate, and then your test outcomes also vary, because, for example, even if you have the same true but unknown parameters, so for example the null hypothesis holds, on occasion you will observe very extreme data and might even reject the null hypothesis. Yeah? So that's a test. To make the notion of this is of course very general, yeah. So it's a mapping from data space to 0, 1, where you have these 2 acts. If one would go into decision theory, one would now basically give some form of utility function to these acts of rejecting or not rejecting the null hypothesis, and this would also make a lot of sense. In statistical testing, actually turns out that we will see later that there is some implicit utility function of what is bad, namely having type 1 errors. But of course, one could make this much more explicit. And if you go into proper decision theory, of course, you assign value or utilities to acting in a specific way under a given state of nature, so under a specific hypothesis. Under a specific hypothesis. But this is not done in the purely statistical viewpoint. There, these X just exist and they are not allocated some form of utility. It's just how it is. Or only this implicit utility that I will tell you about in a second. So what is a standard test? A standard test is like a t-test. A standard test uses a test statistic and a decision rule. So a standard test first evaluates some test statistics, gamma, which you can think in the back of your head like the t-statistic. And then, based on the value of this statistic, uses a decision rule to map the value of the test statistic to the decision reject the null hypothesis or not reject the null hypothesis. And this kind of standard test then is based on the concatenated application of the test statistic and then the decision rule. Yeah. So in terms of so who remembers the decision rule for a t-test? Even if you don't remember how to compute the t-value, but how do you then make the decision of rejecting or not rejecting?
Depending on where we set the significance level.
What?
Depending on where we set the significance level.
Yeah, and if you have a t statistic, what do you do with the t statistic? So what is the exact decision rule? So the significance level is of course something with a probability, but how does that relate to the t statistic?
I mean, if the t-value is more extreme than a certain value that we set, then we reject the null hypothesis.
Yeah, so you basically choose a critical value. So you choose a value in the space of t statistics, which is just the real number. This critical value that you set, as we will see later, that has something to do with the significance level, but you decide for a specific critical value and reject the null hypothesis if you observe t-value is larger than this critical value. But this critical value is not quite the significance level. It's related to that, but we will get there. The thing is, again, everything is random. So the test statistic is random, and then also, because the data is random, the test statistic is random, and then also the application of the decision rule is random. Yeah, this is something we will actually not follow up that much, but then you have the term. The subset of the test statistics outcome space for which the test takes on the value 1 is referred to as the rejection region R of the test. So we assume that the test statistic, and one thing that's important, the test statistic is a scalar value. Yeah? So in these standard tests, the test statistic is a scalar value. And this is important because if you have 10 data points, or 100 data points, or 1,000,000 data points, you compute a t-value that is a scalar value. Yeah, so you compute the average and divide by the standard deviation, which is all summarizing all your 10, 100, 1,000,000 data points, and then you have a scalar value, this the part of the real numbers for which the test rejects the null hypothesis is known as the rejection region. This is important if you study, for example, the probability to reject the null hypothesis. So if you study the event that you reject the null hypothesis, this is the same as the probability for the test statistic to be in the rejection region. So this means that by thinking about, for example, how t-values are distributed, which of course you know because they're distributed according to t-distributions under the null hypothesis, you can make statements about the probabilities of the tests. This is why this equivalence of rejection regions and there are allocated probabilities and events and the event rejecting the null hypothesis are important. Yeah, this is what this says. So the events, the test rejects the null hypothesis, or the test statistics is in the rejection region, have the same probability. And now I'm going really into what is essentially where the t-test is the prototypical test for, a critical value-based test. So a critical value-based test is a standard test with a critical value C dependent decision rule. And this then looks like this. So a one-sided critical value-based test takes the form phi x, that's our test, maps from sample outcome space to 0, 1. To each value in outcome space, we allocate a value of the test. And this is given by the indicator function, which is also defined here. So if you're not used to indicator function, so if you're used to indicator functions, it's a little bit redundant. If you're not used to indicator functions, it's explained here. So 1 with this subscript of this set means that it's this indicator function takes on the value 1 if the statement that you find here in these brackets is true. So if the test statistic is actually equal to or larger than the critical value, then this is 1. You reject the null hypothesis. If it is smaller than the critical value, you don't reject the null hypothesis. So this is a one-sided critical value-based test. You can make it two-sided by looking at the absolute value. So if you think about the t-distribution and you want to reject also if you find a very negative t-value, then if you take the absolute value and reject if it's larger than the critical value, then you just then you achieve that. So if you have a very negative thing, then you take the absolute value, you have a positive, and then if it's larger than the critical value, then you reject. So this is basically this is kind of a general formulation of the t-test. What other tests have you learned about? Has anyone learned about z-tests? F-tests? Yeah. F-tests are actually examples for likelihood ratio tests. Z-tests are fairly similar to this. So the Z-test is also similar to the y-test that we will see later, but the Z-test is essentially the scenario where you know the variance parameter, so you don't need to use the t-distribution, but can use the z-distribution. They work exactly like this. So this is a critical value-based test. There are many more than the t-test, but t-test is an example. So think about it. Using the sample mean and the sample standard deviation, you transform realized data x into the t-statistic, and then you compare the t-statistic to a critical value in order to decide for rejecting the null hypothesis or not. So this is all just definitions, so nothing happened yet. So this is basically, there's not much to understand. It's just the definitions, how things are set up. Sorry, now I just scrolled a little bit around. Of course, things only start to get interesting, and test construction becomes something. If you put some constraints on tests, because right now you could come up with anything and it would be a test, and you would have a test, but you wouldn't know whether it's a good thing or a good test or not a good test. So hence, to give some quality to tests, one looks at errors and error probabilities. And of course, you're very familiar with test errors, because when you conduct a hypothesis test, there always can be two kinds of errors. It can be the case that you reject the null hypothesis, so your test outcome, it should be an x here, sorry, that's an x. I think in my paper it's a y, hence that was a y. X, rejecting the null hypothesis when the null hypothesis is in fact true. So your true but unknown parameter is in the null hypothesis subset of parameter space, but your test says reject the null hypothesis. This is an error and is referred to as a type 1 error. If you, of course, reject the null if you don't reject the null hypothesis when the null hypothesis is true, of course, that's not an error. So this is why this doesn't come up here. And the other error that can happen is that you don't reject the null hypothesis. So your test, again, phi x, says, in this case, 0, when the null hypothesis is in fact false. So your true but unknown parameter is in the subset of parameter space corresponding to the alternative hypothesis. And this is referred to as a type 2 error. Yeah. So, so what are other terms for type 1 and type 2 errors? Yeah, I don't like that much, but any other terms? Yeah, exactly. So this the reason why I don't like alpha and beta is because we will have alpha and beta in a second, and then it has a specific meaning. So type 1 error is also false positive error. So you say something happened, or something is there, when in fact the true state of the world is that there's nothing. So that's a false positive, and type 2 error is a false negative, in the sense something is actually happening and you're saying nothing is happening. So type 1 and type 2 are not really mnemonic, but they were introduced in this nomenclature was introduced in this Nyman Persson paper that introduced uniformly most powerful tests. The important thing now in terms of the utility that I mentioned earlier is that there's this implicit idea that type 1 errors are worse than type 2 errors. So you want to avoid false positive. And once you avoid false positives, you also want to avoid false negatives, but only once you avoided false positives. And this will come up again. The general notion is that type 1 errors are thought about that they are worse than type 2 errors, which you can debate. It's completely debatable, but that's the general view in order to explain test construction, as we will do it in a second. Now with errors, with the test errors come the test error probabilities. And they relate to what you actually just mentioned as alpha and beta. So the way I'm setting that up here is because the test outcome are of course random. Tests are random variables. There is a probability for rejecting the null hypothesis when the null hypothesis is in fact true. So now just relax about the y. I will not draw over it. So y is the data. The probability to reject the null hypothesis when the null hypothesis is in fact true is the probability of a type 1 error, and is also known as and called the size of a test. And the size of a test I denote by alpha. Yeah? So again, the error is to reject the null hypothesis when the null hypothesis is in fact true. This event of rejecting the null hypothesis when the null hypothesis is in fact true has a probability under the parametric statistical model, and this probability of rejecting the null hypothesis when it's in fact true is called the size of the test, and is commonly denoted by alpha. And here this probability theta 0 means that it's the probability under the null hypothesis, so under the assumption that the true but unknown parameter is in theta 0. Then, of course, there is the complementary probability to it, so not rejecting the null hypothesis when the null hypothesis is in fact true. And this, of course, because this is a binary event, so you either reject or you don't reject the null hypothesis under the fact that the null hypothesis holds, is referred to as specificity, and you can evaluate this as 1 minus alpha. One thing that is important to note here, that you often see things written which I really hate, like this. So you see the probability for rejecting the null hypothesis conditional on something like the null hypothesis. And this is really bad because in the frequentist framework, the null hypothesis and the alternative hypothesis don't have probabilistic representations. Yeah? One can do something like this, and one can talk about PPV, so what Ioannidis became famous with, and then say, yeah, because we have too little power, we have all false positive. One can do that, but then one is in a Bayesian setting, and if you condition on hypothesis, then you're in a Bayesian setting and you need marginal probabilities for your hypothesis being true or not. Can all be done, PPV, why most medical findings are false, and this whole literature after that, and the whole debate, but we are not there. We are in the case where the hypotheses don't have associated probabilities. That's important. And this is often, even if people write about frequentist statistics, about tests, they condition widely on hypotheses, and that's all horrible. So we don't do that, hence the subscript here. Then there is the probability of a type 2 error. This is the probability to not reject the null hypothesis if the alternative hypothesis in fact holds. That probability actually doesn't have a name, but it's complementary probability, namely the probability to reject the null hypothesis if the alternative hypothesis holds, so a good thing, and not an error, is called power. Yeah? So the power of a test is the probability to detect an effect when it's in fact there. That is the same as rejecting the null hypothesis under the assumption that the alternative hypothesis holds. And yeah, this is what I said. The size of a test is also referred to as the type 1 error rate. So if you heard about things like family-wise error rate or error rates in general, this is very much related, but yeah, it's called size. And this also happens sometimes. So the probability of a type 2 error is sometimes called beta, and this is where your beta error, I think, comes from. But this, if you look at how power functions are usually written in statistics, namely with a beta, this then goes wrong, and so I don't do that. So power is a good thing. We call it beta. We can have a power function, and then the probability of a type 2 error, we don't call that beta, because then we would have everything 1 minus, and it's annoying. Yeah, because we want to talk about power. And when we call it power, the power function is often denoted by beta. This is one of the reasons why I had to write up all of this test theory, because in every book and wherever you look, it's at one point it always goes wrong. Before the break, I want to finish this general test theory by talking about the significance level, because what you really need to also dissociate in your head is the significance level and the size of a test, which is hard because in terms of the t-test, they are the same thing because they are exact tests, but in general they are not the same thing. So a test is said to be of significance level alpha prime, if its size, or you could also use some other symbol here, but alpha prime is the one that I liked. If its size alpha is smaller than or equal to alpha prime, that means that the probability for a type 1 error is smaller or equal to alpha prime. If it's equal to, then it's actually called an exact test. If the test error rate is smaller, oops, this is of course then also wrong. So that this is correct. This should be a strict inequality. A test is called conservative if the probability for a type 1 error is strictly smaller than the significance level. You might, I mean, depends on how you feel. I mean, we can also have it equal to, smaller or equal to, but the equal, the smaller is the important thing. So a conservative test is not a test where you use a very low significance level. Conservative test is a test which true error probability is smaller than your significance level in a strict sense here. It's called exact if the significance level equals the type 1 error rate. That's for t-tests, that's the case. And a test is called liberal if the test error rate is actually larger than the significance level. Then it's not of significance level in the first place, but to have this notion of a liberal test, we include it. Yeah? But the important thing is to dissociate in your head the probability of a type 1 error, which is called size and denoted by alpha, and the significance level of a test. That is something that you impose, and you want to make sure that usually you want to make sure that the type 1 error rate of your test when constructing a test is equal to your significance level if you create an exact test, or if you that the type 1 error rate is smaller than your significance level if you want to create a conservative test. Of Of course, people don't like conservative tests necessarily because you are even less prone to find something if you use a conservative test based on the significance level that you define. Yeah? But keep these two concepts separated. Finally, the test quality function or power function or end power function, because the power function is a specific part of the test quality function. Somehow I have the y on all of these slides, sorry. Y is x. For a test phi, the test quality function is a function from parameter space into the interval 0, 1 and is defined as the expected value of the test under the probabilistic model of interest and as a function of the parameter, which can of course be either in the null hypothesis or the alternative hypothesis. And we will see how that works in a second. If the parameter is in the alternative hypothesis, then the test quality function is also known as the test power function, and then it's usually written as beta, which maps values of the alternative hypothesis into 0, 1, and then of course this expected value corresponds to, as we will see in a second, to the probability of the test rejecting the null hypothesis if the alternative hypothesis holds. So why does that follow from that? That's fairly straightforward. If you think about in terms of a function of theta about the expected value under the null hypothesis of a test, what you always have in terms of the expected value of the test, that the test can only have the outcome 1 and 0. 0 is of course associated with the probability of the test coming out 0. 1 as the test outcome is associated with the event that the test comes out 1. If you have this whole thing under the null hypothesis, so your theta is in the null hypothesis, then the value of the test quality function is the probability of the test rejecting the null hypothesis under the null hypothesis being true, which is just the probability of a type 1 error, so the size. And if you are in the alternative hypothesis, then this evaluates to the probability of rejecting the null hypothesis when the alternative hypothesis holds. That's then the power of the test. So the test quality function, mainly people are interested in the power function usually. The test quality function is a little bit more general in that you can also look at the size. So you have one function that gives you the size of a test and the power of a test. How this function looks in a specific setting, of course, depends on how these probabilities for these test outcomes really come about. Yeah, but this is the notion of a test quality function, which you need when you want to compute power. Yeah, so computing power is not something about using the G square software, but a G star square software or something. G power software, but it's about thinking how the power function of a test looks like. Good. So are there questions right now? No? Then let's have a break here and then look at an example. Or I guess we will look at these two examples, namely t-test and wall test, and then we do these things, and if there's time we will look at the likelihood ratio test. Okay, so in the last hour we saw the general theory of hypothesis testing under foundations, and of course such general theory is of course abstract and maybe not that easy to grasp, but of course it gets its power from first of all, being able to subsume a lot of specific examples under such a general framework. So meaning that if you understood the general framework, then studying a t-test, an f-test, like a ratio test, variance test, all kinds of tests gets much easier because it's always the same kind of, you always get across the same kind of things. So that's why it's helpful to look at these kind of general theories about certain forms of data analysis. The other thing is also that they, these general theories, like last week when we discussed confidence intervals, they give you a procedure to establish some other, so establish some new confidence interval, or in this week test, if you are asked to do so. Yeah? So if you then are in a applied data analysis setting, and for example you are in biomedicine and they say we need a test for this kind of procedure that we are doing here, and you are able to say something about the distribution of the data, which might not be Gaussian, so you cannot use t-tests. You know how to develop a new test based on the general theory. So this is why I think these general theories are very helpful. Even if you first encounter them, it's a little bit hard to relate them to things that you already know or concrete examples. But this is then the aim of this hour. So, Chuck, we have to go a little bit back. Sorry, here. So based on the general theory, I first now want to introduce the general way of constructing a test. So basically using these general concepts to set up a test. And once we've seen that, we will actually do this for at least the t-test and the wall test. So with regards to test construction, it's again first important to appreciate that people believe that type 1 errors are worse than type 2 errors. Yeah? So this is written up here. So because the type 1 error rate, so the probability for type 1 error is considered more important than the type 2 error rate of a test. Oh, there's a lot of work for you today. Strange. Then the type 2 error rate of a test, the test size is usually fixed first. So you first decide for a test size, for example, by selecting a significance level, for example, alpha prime equals 0 to 0.5, at an associated critical value C alpha prime of the test statistic. Yeah? So the logic is here, okay, we want to do a test. Under a test, we can always go wrong in terms of type 1 errors. So let's make sure we have we keep our type 1 error rate, which is the same as the size of our test, below a certain level. And we can do that by developing a test procedure of a given significance level, because the significance level is always equal to or larger than the size. And often this works, for example, in critical value-based tests by selecting the appropriate critical value. Once the significance level and basically with this the type 1 error rate has been fixed, what people would do is to try to minimize the probability of the test type 2 error, or in other words, maximize the test power. So this is the expressing this thing that if you look into hypothesis testing, and if you look into hypothesis testing, people say we want to do a test of significance level 0.05, and then the thing is, but we have to maximize power, we have to use more participants. The strange thing with the participants is actually that the test power function is defined in terms of the parameters of the statistical parametric model. So if you account for the fact that the number of data points is an explicit parameter in your model, then these power functions that people always talk about make sense. Otherwise, actually, your power function is not necessarily related to the number of participants, because or the number of data points, because you use everything on a fixed sample size. Doesn't really matter. The important thing here right now is that you first fix the size, so the type 1 error rate, and then you compare at a fixed size, so for a fixed significance level, for a fixed critical value, you compare the type 2 error rate and try to minimize that by equivalently maximizing the test power. So based on this idea that first type 1 error consideration and then type 2 error consideration, which is exactly what you did in your analysis, a typical test construction would work like this. So you first define the parametric statistical model. You have to start somewhere. And then you define the test hypothesis, the test statistic, and the test itself. Again, according to what these things are based on our general theory. Then you consider the test statistic distribution. And then, based on the test statistic distribution, establish some form of type 1 error rate control. And once you've done that, you look at the test power function. And what I wanted to do today was to do all 5 steps for T and wall tests. But then last week I was in this committee for selecting the artificial intelligence professor for next year, and then I was quite busy with that, and then I decided I had done enough for the good of data science last week, and decided not to put in the power function development anymore, because I just didn't have the time. I mean, if you want to look at power function development, have a look at my paper. The problem is that it's not done for very simple tests. So I wanted to put it in for these simple tests, but then I didn't manage to. Next year. Yeah, sorry. But I selected good candidates for artificial intelligence for next year. People that do machine learning or data mining, actually. Good, sorry. Other good thing is that you don't have to study the details of doing a test power function. 1 to 4 we will do for t-test and wall test. Likelihood ratio test, I guess not. I first want to make sure that we also discuss confidence intervals and p-values. So now enough generalities. So test construction, parametric statistical model, test hypothesis, test, statistic, test, and then test statistic distribution, and then type 1 error rate control, and this is where we stop. No talk about power, sorry. Any questions? No, good. Then let's have a look at the t-test. Before I start with the t-test, as I hear this construction, next week there will be more construction. So I sent an email around before the lecture. Next week the lecture will happen in another room. I hope you saw that. Now, starting with the t-test. The parametric statistical model behind a t-test is the following. We assume that we have n data points which are uniformly distributed according to a normal distribution with unknown expectation parameter and unknown variance parameter, mu and sigma square. And that's the statistical model. So we have set up the statistical model. That's the first step in test construction. Then we have to set up the test hypothesis, the test statistic, and the test. We are interested in formulating here a test for the expectation parameter. So we partition only the expectation parameter space. The expectation parameter is, of course, mu. The parameter space are the real numbers. And in this case, we consider the test hypothesis that the true but unknown expectation parameter is in theta 0, which only contains one value, namely mu 0, and the alternative hypothesis that the true but unknown parameter is in theta 1, which is the parameter space without this mu 0. Yeah? So this is the partition of parameter space, and this is a simple hypothesis, and this is a composite hypothesis, but that's just further nomenclature. And then one can construct a two-sided test by using the test statistic T, which is the T statistic, which we have seen previously is defined as the square root of the number of data points divided by the standard deviation, the sample standard deviation, sorry, Sn, times the sample mean minus the true but unknown parameter. And last week when we talked about confidence intervals, the good thing was that mu0, if we talk about confidence intervals, goes away and in the distribution, and we can basically then create a confidence interval around this true but unknown value. So it doesn't hurt that the t-statistic requires the true but unknown value. And this week when we talk about test hypothesis, of course, we can look at the t-statistic distribution under the assumption of one of these hypothesis. So again, it doesn't hurt that the t-statistic involves this mu0, because if we look at the distribution of the t-statistic under the null hypothesis, we know what mu0 is, and yeah. And we actually don't look at the at the distribution of the t-statistic under the alternative hypothesis because we don't do power. So don't worry about this mu0 here. That's what I'm trying to say. And based on the t-statistic, we can define the test, reject the null hypothesis if the absolute value of the t-statistic is larger than some critical value, and don't reject it if it's not. So now we have defined test hypothesis, a test statistic, and a test. We haven't said anything that this is a good thing, but we have defined these things. Then, if you want to continue with the construction of the test, of course, the aim is then to somehow keep the type 1 error rate of this test at bay or under control. You need to make a statement about the distribution of the test statistic. Yeah? And of course, the distribution of the test statistic depends on the test statistic. In this case, we use the t-statistic, and we know that under this parametric statistical model, the test statistic, namely the t-statistic, is distributed according to a t-distribution with n-1 degrees of freedom. We discussed that last week, and hence under the assumption under the null hypothesis, so that the true but unknown value is in theta 0, it's distributed according to a t distribution PDF with n-1 degrees of freedom. Yeah? That's last week's stuff. And this is always what you need to do when you establish a test. So first you define a test statistic, and then you need to make a statement about its distribution to then be able to say what's happening under the null or and or the alternative, usually then also the alternative hypothesis. And again, random variable transformations. Yeah? So a statistic is a function on the data. The data are random variables. If you want to know how the test statistic is distributed, you need to know how the transformation affects the distribution of your data. It's a little bit more. Now, type 1 error rate control. If you know what the distribution of the test statistic is, then you can, of course, now come up with a decision rule that is of this form by thinking about the distribution of the test statistic. And we know that the t-statistic is distributed according to a t-distribution. We know its PDF, we know its CDF, and we can hence find a value, a critical value, such that we leave we can find a critical value such that if we reject only if our observed t-value is larger than the critical value, there's only a certain probability for this to happen. To make this a little bit clearer, I can draw on this, to make this a little bit clearer what's happening here, because intuitively it's horribly simple. We have the t distribution here, and we want to reject, we want to leave 5% for errors. So we use a critical value C alpha prime such that the rejection probability is here 0.025 and here 0.025. And what is written up here in terms of the inverse of the CDF, and this is just going from the probability of this is the CDF, to go from 97.5 to the corresponding value in T space, which is the critical value. So this is just this is very intuitive. You've seen that for t-tests before. It just takes, if you follow the notation through in terms of the CDF, it is written like this because you need the inverse of the CDF. You need to make the cutoff at half your significance value, because you also want to, because we are using this two-sided test here, that you also reject if you have a negative value, which you can do because the for t, because you have this symmetric t distribution. So to make this explicit, for example, if you have 10 data points, you want a significance level of 0.05, then your critical value is this inverse CDF evaluated at 0.975 for n-1 degrees of freedoms, and you get a critical value of 2.26, which you also remember that for if you go to high degrees of freedom in the t distribution, you are where you are with the normal distribution, so it's around 2, 1.96, and if you are at lower degrees of freedom, so fewer data points, you need larger t values to reject. Why this with the significance level and the error rate here works that nicely is because your first of all, everything is invertible, so your CDF you can invert, and you have a very so you have an exact description of your of your test statistic distribution, and this test statistic distribution has a PDF with a CDF that is invertible, so you can directly compute the critical value. In other settings, when so for example in brain imaging, where you have test statistics that refer to cluster sizes and so on, and you also have approximations for the probability of these cluster sizes, that's one example that I know, you might find the critical value not by or you find the critical value by numerically inverting the CDF, so you basically just increase the critical value until the probability falls below some value, and then you have found your critical value numerically. This is how we did it in the paper. So this is a special case. This is a little bit like math in school and math at university. In school, you always do these special cases, and then it's hard to understand math at university because it's not only the special cases. And this is the same thing here. You're very used to the special case. It's a special case that is specific to the t distribution and also the normal distribution, but it's not how things work in general. Anyway, this is how you can control type 1, the type 1 error. And now what you would have to do is, based on this critical value, think about the probability of rejecting the null hypothesis when the alternative hypothesis holds, and evaluate the power function. And for this, you actually need the distribution of the test statistic under the alternative hypothesis, which is a non-central t distribution. And all this stuff I didn't include anymore because I spent a lot of time in this committee last week. Sorry. So no power function. But at least we controlled the type 1 error rate. Questions about the t-test? No. Good. Then the wall test. This we could have done before this, because in a way it's simpler because it doesn't have the t-distribution. On the other hand, it's more general than t-test, so I put it after it. So the wall test obviously used the wall statistic that we've seen already last week. Does anyone remember something about wall statistics? No? Okay. Anyway, The parametric statistical model that we are considering here is a random sample from a parametric statistical model with unknown parameter, scalar parameter theta. And we are not making any specific assumptions about the form of this parametric distribution, but we assume that we have an asymptotically normally distributed estimator for theta, for example, the maximum likelihood estimator. Yeah? So remember that the maximum likelihood estimator is asymptotically normally distributed. We used this last week to construct approximate confidence intervals based on the standard normal distribution. Yeah? Hope you remember that. And we looked at that in some detail when we talked about asymptotic estimator probabilities in terms of the proof that the maximum likelihood estimator is asymptotically normally distributed. So we did quite a lot. We actually also last week in the Übung, we saw that the maximum likelihood estimator for Bernoulli distribution is asymptotically normally distributed. No? So we've seen this before, the general idea. Now, we again start with, based on the parametric statistical model, to define the test hypothesis, test statistic, and test. So same procedure. The test hypothesis being, again, a simple hypothesis where we could also put some brackets around this, although sometimes this is not done to make sure that this is a set. And now we use the test statistic Wx, which is given by the observed expected Fisher information at the location of the maximum likelihood estimator and the square root of that times the maximum likelihood estimator minus the true but unknown parameter value. And this is what we established 2 weeks ago, I think, or 3 weeks ago, to be asymptotically normally distributed for a large number of samples. And so that's the Wald statistic, hence also the Wald test. There are different versions of the Wald statistic. As you remember, we've seen, I think, last week, where I also had IN here. Here we use the expected Fisher information. And for this test statistic, we again use the same test decision rule, namely reject the null hypothesis if the Wald statistic is larger or equal to the absolute test statistic, the absolute Wald statistic is larger or equal to then some critical value. Now the next thing is to consider the test statistic distribution, where we have seen previously that the Wald statistic is asymptotically normally distributed, and its asymptotic distribution is given in terms of the PDF of the standard normal distribution. Yeah? So this is actually in a way easier than the distribution of the t statistic, because it doesn't involve the t distribution, but only the standard normal distribution. In a way, it's like a z-test, but with the difference that this is only an approximate test, where in the z-test, of course, the assumption is that the data are normally distributed with known variance parameter. Here we don't have the assumption, this is important, we don't have the assumption of normal distribution about the data, but we have the assumption that we have an estimator that is asymptotically normally distributed, which maximum likelihood estimators are. And then we can, like for the t-test, use the inverse CDF with the same logic to find a critical value and only reject if our test statistic is larger than this critical value to again control the size or the type 1 error rate of the test. And then we have created a type 1 error rate controlled test, which is known as the Wald test because it uses the Wald statistic. And it's a test that you can always use like the confidence interval with the Wald statistic if you have a maximum likelihood estimator and n is relatively large. Yeah? So see this in direct parallelism to the confidence interval for the Wald statistic last week. Of course, the same thing for the t statistic. Yeah, questions about the Wald test. So that's an approximate test that is fairly versatile because you can always use it if you have a maximum likelihood estimator. Now, what would be interesting to discuss are likelihood ratio tests, because likelihood ratio tests, of which the f-test is a specific form, can be shown to be the most powerful tests that you can use if you have simple hypotheses. and this is known as the Nyman-Person lemma. So if you have simple hypothesis, meaning that your null hypothesis and your alternative hypothesis only contain one value for a parameter, then the likelihood ratio test is the most powerful test. It's actually uniformly most powerful for all different parameters under a given for a given, of course, critical value. And this is what is known as the Nyman-Person lemma. So there you don't, for a likelihood ratio test, you don't really need to think about the power function because it's already guaranteed to have maximal power in this class of tests. However, to introduce all of this, it needs a little bit, and I will not go over this right now because, yeah, we don't have the time. So, likelihood ratio tests, unfortunately, also not discussed here. Thing is, at one point I have to, of course, cut things because one could do like half a term on hypothesis testing, but we also want to talk about other stuff. So we are leaving out likelihood ratio tests. If you ever read Nyman-Person lemma, that's related to likelihood ratio tests. It relates closely to what we discussed here, but they have maximal power. For the remainder of this lecture and what we do this year, I want to first discuss the duality of confidence intervals and hypothesis tests, because this ties what we did today nicely together with what we did last week. And then finally, we talk about p-values. Good. So we've seen now two examples for tests, and now we want to talk about how tests are related to confidence intervals. Because somehow we've seen what we did today already last week. So we looked at the t-statistic and used it to construct confidence intervals, and we looked at the wall statistic and used it to construct confidence intervals. And now we use the same statistics, the t-statistics and the wall statistic and their distributions, the t-distribution and the standard normal distribution for tests. So can this somehow be related? Yes, it can. And this is kind of the basic theorem about this, and it tells you how to construct a test based on a confidence interval or to construct a confidence interval based on a test. So this is what this is basically relating. The basic assumption is, of course, the same as in both cases. So we have a parametric statistical model, we have a random sample and data points outcome space, and we have a PMF or PDF. And now we start again with what we started with last week. So we assume that we have a delta confidence interval for theta. So we have this lower bound and this upper bound, and we assume that this confidence interval has this coverage probability of delta for the true but unknown value. Then what we can do, I think that I corrected that anyway, there needs to be a comma. What we can do based on this confidence interval, define a test. And this test we define as follows. We do not reject the null hypothesis if theta is in the confidence interval that we computed, and we reject the null hypothesis. We do not, I was say these binary things the wrong way. We do not reject the null hypothesis if theta is in the confidence interval that we compute, and we reject the null hypothesis if theta is not in the confidence interval. This is the test. It's of significance level alpha prime 1 minus delta. And the important thing is following now. It's a test for the hypothesis, and maybe I should have put the hypothesis up first, for the null hypothesis that the true but unknown value is theta, and the alternative hypothesis that the true but unknown value is different from theta. Yeah. So basically how this works is you first create a confidence interval for theta, then you say you want to test the hypothesis, and this is why I should have maybe put them up first. You say, okay, I want to test the hypothesis that theta is, for example, 2, And then you use the test that if 2 is in a confidence interval that you computed, you do not reject the null hypothesis, and you reject the null hypothesis if it's not in there. And the significance level of this test is then 1 minus delta. I will show you why that works in a second. First, the other way around. If you have tests of significant, exact tests of significance level alpha prime for the hypothesis that the null hypothesis theta being theta, and maybe I should have used a theta 0 here, the alternative hypothesis theta not being this specific theta here, and you can actually write the non-rejection region as an interval. If you can write the non-rejection region as an interval, then this is a confidence interval. So again, first showing that this holds, and then maybe I first show you an example to make this concrete, and then I'll show you why it works. So let's look at an example, because then I think it gets clearer. And this is an example for constructing a test based on a confidence interval. You can, of course, also construct confidence intervals based on tests. The whole thing is about inverting one or the other. And we go now from a hypothesis test, we go from a confidence interval to a hypothesis test. So we start with a confidence interval and create from it a test. You could also go from a test to a confidence interval, but we go this way around. So, and this goes back to what we did last week. So we have previously shown that for a normally distributed random sample with unknown expectation parameter mu and unknown variance parameter sigma square, typo mayhem today, a confidence interval is given by this. Yeah? So we've seen the last week, so I don't explain it anymore. Now we can create a test for the expectation parameter for the hypothesis, null hypothesis theta 0 being equal to mu by rejecting the null hypothesis if our mu of interest, that is our null hypothesis, so not rejecting the null hypothesis, if our hypothesis mu is in this confidence interval, and rejecting the null hypothesis if our hypothesis mu is not in the confidence interval. Yeah? So concretely how this would work is if you say, for example, my mu is 0, I use this confidence interval, and my confidence interval covers 0. So for example, my confidence interval is -1 to 2. Then I would not reject the null hypothesis. If my confidence interval that I compute based on some data is, for example, 1 to 3, then I would reject the null hypothesis. And the important thing is not so much about this procedure. This is the procedure that works, but the important thing is that if my confidence interval is a delta confidence interval, so for example a 95% confidence interval, then the test procedure that I'm using here has a significance level of 1 minus delta, so 0.05. Yeah, and that this holds. This is based on this proof here. So if you go from the test, so you say we have a test of significance level alpha prime, then alpha prime is equal to or larger than the size of the test. The size of the test corresponds to the event that the test rejects the null hypothesis, or rejects the hypothesis under theta, and this refers to our null hypothesis here. And this rejection is defined here as not being in the confidence interval. Yeah, so this is that this equality here just falls from the definition of the test, And theta not being in the confidence interval is, of course, the probability for that is, of course, 1 minus the probability that theta is in the confidence interval, and this was defined as delta. Yeah? So if you understand this chain of equalities here, then you understand why this works. And it works just because the test is defined like this. Yeah? It works because the test is defined to reject the null hypothesis if the parameter of interest is in the confidence interval. And the other way around, if you have a confidence interval of a level delta, then this means that if theta here is your null hypothesis value, the probability for theta to be in the confidence interval that was delta in the first place, this then is the same as not rejecting the null hypothesis in terms of the test, because that's how it's defined. And the probability for rejecting the null hypothesis under the assumption that the null hypothesis is true is then the complementary probability of this, and this is hence 1 minus alpha prime. We could have also yeah, because this is actually there should be a larger equal there, because this is alpha. Yeah, so this is the probability for rejecting the null hypothesis if the null hypothesis holds. Yeah? So the bottom line is delta confidence intervals can be used to construct tests of significance level 1 minus delta. Tests of significance level alpha prime can be used to construct 1 minus alpha prime confidence intervals. And in this sense, confidence intervals and hypothesis tests are equivalent. So they are not equivalent like it's the same thing. They are the same thing if you, based on a delta confidence interval, define a test like this, or based on a test and the lucky fact that the test non-rejection region is actually an interval, which it doesn't need to be always. Then, so for example, in the t-test, in the t-test it actually works, of course, in the two-sided t-test, because the non-rejection region is the middle part and it's an interval. So then this is equivalent, and you can use it as a confidence interval. Yeah? Questions? No. Good. Then we have 5 minutes left for p-values. A little bit sparse. How do we do it? Yeah. So in general, now I think we don't. I think we don't discuss p-values now in detail, which is a little bit of a shame. They are important, but then on the other hand, they can be either really simple, or we can introduce them a little bit more complex. So the thing with p-values is that they are just more richer than to report p-values than to report the outcome of a test. If you report the outcome of a test, you would say, I rejected the null hypothesis. You would say 1 is my outcome. The other outcome of a test is I didn't reject the null hypothesis test, 0 is my outcome. Now, of course, when you evaluate a t-value, for example, you have at the same time if you evaluate a t-value, let's not do that. You get a t-value here, and irrespective of whether you use some level of significance or not, you can of course ask what is the probability to observe a t-value more extreme than the one that I observed. And this of course can be any kind of value. It can be, for example, 0.03. And if you, in this case, you can of course equivalently do your rejection not based on the critical value, but you compare the p-values. So this is what I actually introduce here. The thing is, if you, in addition to reporting the outcome of your test, you report the p-value, you just report more information. So you basically then also allow the reader to define their own significance level, because they could say, okay, you rejected, so you report this and you reject the null hypothesis at a significance level of 0.05. So you say reject, my test outcome is 1, but you also tell the reader the p-value. Then if, for example, we report that the p-value is 0.003, then the reader can say, based on this, I can also reject the null hypothesis at a significance level of 0.005. And based on this logic, the p-value is always defined as the largest value over parameters in parameter space, such that the value of the test statistic as the probability of the test statistic to be larger than the observed value of the test statistic. But I think we should stop here. Who wants to learn more about p-values? Then we go about this next time. Who wants to learn more about non-parametric statistics? Then we only do non-parametric statistics. So let's decide this now. Who wants to next week start with p-values so that you understand more about p-values? Okay, you are not interested. I like that. P-values are a little bit annoying. So, okay, then next week we will start with p-values, but then we will have to cut something from non-parametric statistics. And I'm not quite sure what yet, but maybe we cut. What do we want to cut from? We have to cut something. Anyway, or we just make more. We just take longer.
Or we can read the materials after class.
You are always invited to do that, of course. Good. So then we stop here. So yeah, appreciate from the outline of the lecture. This is foundations. You can always use this, and it's important, and read it and understand it, so then you can understand all tests. These are examples, and this the confidence intervals and hypothesis tests should help you to study confidence intervals and hypothesis tests in one go. So if you are clear about t-statistics, wall statistics, then you get the whole hypothesis testing and confidence intervals in one thing. Good. So then let's stop here and continue 20 past with the other people.